So there's two important terms that we need to bring up to clarify the reason for doing implicit approaches, which we're about to talk about in more detail. One of them is convergence and the other is stability. Convergence refers to the solution approaching the true solution as delta t and delta x go to 0. So let's say delta t, so delta t and delta x get smaller. The finite difference method, or I mean, this can apply in general for any method. Method approaches the analytical or the true solution. Okay, that's what convergence means. And stability means that in each step of the computation, says the computation proceeds errors get smaller. Okay, that's not generally true, and we saw instability problems. For example, if you'll remember iteration, when we did fixed point iteration, we saw stability problems where we got the error getting bigger and bigger. In root finding, we saw cycling where the error was fluctuating or oscillating. This is a problem too in this method if certain conditions aren't met. The finite difference method with the explicit approaches, if certain conditions are not met. What are those conditions? Well, the condition is basically if lambda is less than or equal to 1/2, then and this is better wrote. So remember that lambda is equal to k delta t over delta x squared. So probably a better way of writing this, because it makes more sense, is that if delta t is less than or equal to 1/2 delta x squared over k. So if this is true, then the method is both convergent and stable. Now, even if it's stable doesn't mean it's not going to oscillate. Stable just means well, it could oscillate, but for delta t less than or equal to 1/4 delta x squared over k, this is the error, the solution, we'll put it this way, solution does not oscillate. So that's even better. And it can be shown that if delta t is less than or equal to 1/8 delta x squared over k, then this minimizes, or it tends to minimize truncation error. Truncation error. Remember that sweet spot between truncation error and step size. That's what we're talking about there. So that delta t is usually what we're looking for. Well, actually, this is wrong. I wrote this wrong. Delta t, when it's equal to that tends to minimize truncation error. Well, this is problematic. Oh, sheesh, I made another mistake. So correcting this mistake right now before it goes up. This is 1/6. Okay, let me double check. Yes, this is true. So this is the whole reason then the convergence and stability issues. This is the whole reason that we need to introduce implicit methods to take care of this problem, because implicit methods, as we found before when we were doing ordinary differential equations, don't suffer from the same problem that explicit methods do.